Okay, I will talk about proof of channel capacity theorem. This note aims to give the proof of channel capacity theorem. It has a forward and converse part, two parts. And for the forward part, I will divide the lectures into 4 videos. So here is the setup part. We need to learn the language used in the proof. So here, the first one is a message index set, W. Script W is a set of integers from 1 to m. M here is the number of messages in the message set. So m here is the number of messages in the message set. Message set in this message set W, and when we take log 2 of m, is number of bits each message carries. Okay, and if we let m is equal to 2 to the power of nr, so this is going to be the number of messages, and where r is going to be the number of bits per single channel use. If you use one channel, then this much information bit is sent. So for let's take an example. Let's say m is equal to, let's say, 8, and suppose that we use n is equal to 6. So we use channels 6 times, and let's take a look. And if we take log 2 of m, log 2 of this is 3 bits. So this is 3 bits per messages. That's the 3 bits per message. And if we use the channel 6 times, then rate R is what? We use it 6 times. Log 2 of m divided by n is equal to 6. Then this is going to be 3 divided by 6. So this is going to be the number of bits per channel use. So that's the rate and its relationship to m, the number of messages, and its size of the message set or the index set is equal to m. Okay, so it should appear right here. And if we have m messages, it can be enumerated from 1 to m. Okay, so that's the relation. All right, so that is about message index set. So a message is selected and sent. It is represented by a uniform random variable W over the index set, script W. So if, let's say, m is equal to 8, W is selection random variable. each message is selectable with equiprobable manner. Okay, so W in that particular case where n example where n is equal to a, W can be selectable and with the equiprobable manner like that. So it can be selected. It can be 1 with the probability 1/8, 2 with the probability 1/8, 8 with the probability 1/8. So that's selection random variable. So our message can be selected with equal probability. And once you have selected a message index, then that means a message is selected. So for example, what is the difference between message and message index? So here I can, in the example of m is equal to 8, I'll have message itself. So message itself, for the case of m is equal to 8, these messages. These are the messages. For example, okay. So these are the 8 messages. So that's a message itself. And what do we mean by message index? If we use this message itself, it will be very long. So we need to have means to describe it shortly. So we give a name. So index. This is our first message, second message, third message, fourth, all the way up to 8. So this is what I mean by indexing. Okay. So this is message. This is message index. So we can we have enumerated the messages. So we can refer to each one of them with this simple messaging. Okay, so that's difference between messaging and message index. So they have one-to-one relation, one-to-one correspondence relation. So once you know the index, you know the message itself. Okay, then using the message selection random variable W, we can select a signal to send, over the channel. So the signal is the n tuple, right? Is n-dimensional factor, and in the case, and we need m such signals for each index W, right? So here W is a random variable, and the xn itself is a function from random variable W to signal, and n is the number of channel uses. So a signal is represented by xn. The received signal is y of n. In fact, the signal that we send is going to be a code word. So we can use it interchangeably, a signal and a code word in this note. The channel is given by the conditional probability distribution, as we have seen in channel capacity proof. I mean, channel mutual information based channel capacity, and there is alphabet X and alphabet Y. So based on which channel you talk about, this X and Y are going to be given with the conditional probability distribution. So, for example, X could be binary 0 and 1, and Y also 0 and 1, or Y could be 0, 1, and eraser, or Y could be Gaussian distributed, real value, for example. Okay. And then we have this conditional distribution given, and that's going to be the channel. So a signal selected to be sent at the transmitter, this is going to be it. When an index is determined, then we are sending the wth messaging, and then we are going to select a signal using this function xn. So xn is again another random variable. Using this selection, using this signal selected, this manner is going to go sent over the channel, and you will receive yn. How do you receive it? Basically, use the conditional distribution. Once you have received this yn, then you make a decision using the decision function g. So using g, you made a decision, and then you get an index w prime. So the w prime is a number in the one number in the message index set. So this is script W. Okay, so that's the whole process, going from signal selection, message selection, and then according to the message, you select a signal, and then you send over the channel, you receive signal, which is yn, and then you make a decision based on yn. And then once you made a decision, you get the index back. Okay, so that's the whole procedure, and that is explained in this picture. So W index, and then you do the encoding, then you get X of n, n-dimensional vector, element of which is taken from the alphabet X, script X, and you send over the channel, you receive yn, and then you make a decision on the possible transmitted index, which is W prime. Okay, and error occurs when W prime is not equal to the transmitted index W. So here we have to talk about number of channel uses. We will deal with the discrete memoryless channel. And this channel is the same channel is used independently and repeatedly. The same channel is independently and repeatedly used. So a discrete channel, one of them, is a 3 tuple. Script X, the channel input alphabet, and channel output alphabet, Y, script Y, and the conditional distribution. This discrete channel is used n times consecutively. Each use is IID, and it is the nth extension of DMC channel. The simple channel is used n times. That's what the meaning of this word. And we call it vector input, vector output, conditional distribution. And this vector input, vector output, conditional distribution is nothing but product of each channel n times. This one is parameterized by the time index I. So the first channel use, second channel use, third channel use, but in fact this is actually identical distribution. So we can ignore this index. But this is to show the channel in general. If it is not identical, if it changes, then, but the channel use is independent from one channel use to the other, then this is, this expression holds in that general, more general case. Okay, a code with the rate R. So on M and N code, M is 2 to the power of NR. Code for DMC channel has this many code words. So this many messages, and for each messages, you have a corresponding code word where the code rate R is defined to be this number. Okay, so log 2 of M divided by N. We have done the example a moment ago. So this is going to be bits per transmission, single signal transmission, single X transmitted and Y received. That's one channel used. So we are using this discrete channel n times. So we need to divide it by n, or we can just say that this per channel use. So this is a channel, we use this channel n times. How many information bits or message bits are we sending over this n channel use? That's the rate of the code. An encoder is a function, xn, which assigns an n-dimensional vector to an input index w. So xn is selecting an index from w and assigns a signal or code word. Okay. The element of code word is taken from the alphabet X. And then we are, this vector is n-dimensional. A code book is explained here. For each index I, the encoder does this assignment. So output of the encoder is n-dimensional vector. Okay, so xn here is like a random variable as well. So it will have certain distribution to select this code word. And after the selection is made, I use a small letter x to describe that this is the deterministic So after you have already made a selection. This is not random variable anymore, but this is just a n-dimensional vector to represent the message index I. Since I have m messages, thus I have m code words. So there are 2 to the power of nr code words in the code book. So we collect all these code words into a matrix, then we can form a code book matrix. So we can collect this into a matrix, and we can say, let's say X, we can say this is a code book. First code word using the first code word using channel n times. So this is a small letter. If it is a capital, we have made a selection. If this is a small letter, then we made a selection, and these are numbers. So X and second code word all the way up to X and so empty code word. So the number of rows is 2 to the power of nr. Number of columns in this matrix is n. Okay, so I have 2 to the nr by n code book matrix. 2 to the power of nr by n code book matrix. This will represent code book or a code. So we can use this as a code. If this is a capital letter, I have made a selection. If we made a selection, then this is a deterministic code book or deterministic code. Okay. So if we let this as a symbol C, this symbol C means that this is a random matrix whose dimension is this. Once you made a selection, then this is going to be a 2 to the power of nr by n deterministic matrix. Okay. All right, that's about code book. So you receive, you send one of the code words, and then you will receive yn, and upon receiving yn, you make a decision on the index, transmitted index. That's the function g, which is the decoding function. So decoder is a function from yn to index. And the probability of error for the ith message. So you send the ith message at the transmitter. What is the probability of error? The probability of error is that the transmitted index is I, and your decision is not equal to I. Given the selection is made. Okay, so using the description so far, the definition so far, this occurs when you receive the signal as so many errors. It is significantly different from the transmitted word. So that's going to be described by this conditional distribution. Okay. So that's a summation of over all yn, and this is an indicator function. So this indicator function says that you made a decision. That decision is not equal to the transmitted index I. And this function, indicator function, is in such a case, this is 1. And other cases, which is the complement of this set, occurs, then it is a 0. So this is 1, 0 function. So indicator function over set S means is defined to be 1 over the set S. Okay. Hold on a sec. And 0 otherwise. Okay. So probably I need to say when omega belongs to set S, then it is 1. When omega does not belong to S, then it is 0. So we can write this the same way that we have used this so far in this class, where yn belongs to the set of yn, such that the decision g of yn is not equal to I. Okay, we can write this way as well. So that's the explanation for the lambda I. So we will define lambda I to be the probability of error for the ith message sent. Okay, so ith message sent, lambda I represent the probability of error. All right, the probability, maximum probability of error, lambda superscript parenthesis n, it is defined as maximum lambda I. Okay, so among all I, what is maximum lambda I? That is the maximum probability of error. Okay. So the probability of error, finally, is the average lambda I of all equiprobable message index I. So we use message equiprobably, and take the summation of all lambda i's, and that's the average probability of error, PE, superscript n, and this one should be smaller than or equal to the maximum one lambda n. So maximum, lambda superscript n is maximum of this lambda I, right? So maximum number is greater than or equal to, is greater than or equal to the average. Okay, so that's the probability of error. So I have talked about almost everything about this picture. Index selected that can be described by this random variable W. Encoder gives a code word for each index I, and one of the code word is then sent over the channel using this DMC channel n times repeatedly, consecutively, and you will receive yn, and then upon receiving yn, you made a decision on the index transmitted. We will call it W prime, and we have talked about probability of errors for this event. Okay, so we have complete the setup using the languages that we have developed so far. Okay, so we say the rate R is achievable if a code with a vanishing probability of error exists. Okay, so we can choose any R without worrying about probability of error. In such a case, the rate R you can select, but it may not be achievable. So we say rate R is achievable if this condition satisfied. So basically, probability of error for such a code should be approaching 0 as you increase the number of channel uses. Okay, I have talked about this, and we say a rate R is achievable if there exists a sequence of codes. I use 2NR and taking the integer, the ceiling operation. So this is a ceiling operation. Okay, so taking the ceiling operation. So for example, if this number is a fractional number, let's say 18.16, let's say 15.8, and if you take the ceiling, this is 16. Okay, so there exists a sequence of codes with the maximal probability of error, or the probability of error tends to 0 as n goes to infinite. So that's the channel capacity, the basis for channel capacity theorem, and that is what we mean by achievable rate R. So this actually is achievable rate R explained. So if rate R is achievable, that's if that is given, then we have to show with such a rate we can find a sequence of codes with the probability of error tends to 0 as n goes to infinite. Okay. So that's the message, and the capacity channel capacity theorem says that achievable rate R has to be smaller than or equal to channel capacity C. That's the message. Okay. The capacity is a supremum of all achievable rates. And if R is smaller than C, then the probability of error can be made vanishing to 0. Okay. Converse is that if there is a code with the probability of error converging to 0, then rate has to be smaller than or equal to C. Okay, so forward and backward.